Hi everyone, this video is going to cover common pitfalls that you may have made on the Key Assessment Unit 3 chemical reactions. So let's go ahead and dive into question number 1. Question number 1 was asking you for all of the reactions listed, part A, B, and C, to add coefficients in order to balance the reactions. It also specified that you must show all of your work. Here, I have added in all of the coefficients, but of course, to earn full credit, I do need to be uploading that work sample. So what exactly do we mean by showing all of your work? You should be showing your atom inventory. That would be this part right here, the atom inventory. And then as you play around with the coefficients, as you add the coefficients up here, you should be updating your atom inventory. You can see that here by the cross out and then the new number. Remember that your goal is to show conservation of mass, meaning that the total number of atoms of that element in the reactants should equal the total number of elements of that reactant in the products. One common pitfall that I noticed is when putting a coefficient in front of a molecule, remembering that that 2 in front of AlCl3 goes both to the aluminum and the chlorine. So that means that I have 2 aluminum and I have 2 Cl3s, a total of 6 Cls. So make sure that you are applying that coefficient to the entire molecule. Another common pitfall that I saw in part B over here, part B, you actually in the products, you had oxygen show up in 2 places. So remember that we are totaling in our added inventory. So this is the total number of that type of element in your products and the total amount of that type of element in your reactants. Taking a look at the rubric for this, in order to earn full points here being a 5-6 category, you needed to get all 3 of the equations balanced correctly and have all of your work shown correctly. If, let's say, you missed one of these balancing equations or made some mistakes in your work, that could put you into the 3-4 category. Or if you balanced all of these incorrectly, or maybe only got one of them, or you did not show your work, that would be a 1-2, not meeting expectations. Scrolling down to number 2 says Einstein was trying to balance this equation, and here was Einstein's work. And notice that Einstein has changed the subscript of H2O to H3O. Explain why Einstein cannot change the subscripts in order to balance the reaction. He can only change the coefficients, and be as specific as possible. Okay. So there are really 2 important things to address in this question. The first important thing to address is why not a subscript? And the second important thing to address is why can you change a coefficient? So we're going to start building this answer by discussing what a subscript is and what a coefficient is. A subscript here is going to be the number of atoms that are bonded together to make up the molecule. Excellent opportunity to show off some vocabulary here using words like atoms and molecules. And a coefficient is referring to the number of molecules themselves. Okay. Now, if we were to change a subscript, like Einstein did here from H2O to H3O, this would be a change in my overall molecule itself. Notice that H2O was water, H3O is some totally new substance. This changes the substance and changes the properties that come along with the substance. However, if you change a coefficient, you are not changing the substance. Instead, you're just adding more of the same. It's kind of like when you're baking a cake, you're making that batter. You're working with all of the same ingredients, but you're allowed to add more of some ingredients to get it to the right consistency. Some of you in your answers even decided to come back up here and correctly balance the equation. The correct way to balance this equation would be by adding coefficients as seen here, but note that you did not have to do that for this question in order to earn full credit. So let's take a look at the rubric so that you better understand where this is coming from. In order to earn full credit over here in the 5-6, that's our highest category, you needed to explain both the subscript and the coefficient to be very complete. If you only explained either the subscript or the coefficient, that would put you in a 3-4 category. Or if you simply missed the mark, there was a lack of evidence about how to balance reactions, you would have been in the 1-2 category. And moving on to question 3. Question 3, you are given this reaction of sodium sulfide and hydrochloric acid, yielding sodium chloride and hydrogen sulfide. You are told that this is a double replacement reaction and asked to justify why this is a double replacement. So this is a really great explain question. Many of you listed the general equation for double replacement reactions, AB plus CD yields AD plus CB. This is a really excellent start, and from here you need to talk about how this actually applies to the reaction that we've been given. For example, listing that A stands for sodium, Na, that B stands for sulfur, C stands for hydrogen, and D stands for chlorine. Another way to make this connection between our general equation and the reaction provided in this question is to use colors. So highlighting in the general equation A, B, C, and D, and then following that through in the actual reaction for our question. Another approach that doesn't involve the general equation is simply to discuss what's happening, what is replacing what and where. So many of you talked about how the Na was replacing the H and the H replaces the Na and kind of talked through the reaction in that way. Totally fine. This would earn you a 3-4 so far, but we need a little more detail in order to really justify what's happening. One detail that you should be thinking about is how in the reactants, you must be breaking apart bonds. You're breaking apart A from B and C from D. So you are breaking bonds. Some of you said breaking intramolecular forces, also fine. And then once you break apart A from B and C from D, you reform those bonds or reform the intramolecular forces in order to get AD and CB. So talking about the bonds, talking about the intramolecular forces will help you get into the 5-6 category. You'll notice that the highest category here, though, is to earn a 7. To earn that 7, you really need to be zooming in on the forming of bonds over here and talking about which atoms can form bonds with which other atoms. And this is where a recognition of positive and negative ions really comes into play. We know that in a molecular formula, you always list the cation or the positive ion first. So that means that our positive cation must be A, paired with a negative anion, B, and then C, a positive cation, paired with a negative anion, D. The reason why this rearrangement can happen, this replacing A and C with each other, is because A, our cation, in the end is paired up with D, which is another anion. And C, our cation, is paired up with B, a different anion. So what you should be noticing is that you always need this cation and anion pair, or a positive paired with a negative. Remember what this is talking about. Remember back to Unit 2, our bonding unit. cations really like to give away electrons in order to be happy and full. Anions really like to take on valence electrons to be happy and full. So this is why cation-anion pairs come together. They make a really good pair for ionic bonding. Discussing the charges or using the words like cation and anion, discussing how those are paired together, that would earn you a 7. Moving on to question 4. Question 4 is a throwback to the Hindenburg disaster that we focused on in Unit 2. We are told that the Hindenburg is a chemical change. Another way of saying this is it is a chemical reaction. We are asked in Part A to provide macroscopic evidence, the stuff that we can see or feel or smell, as well as microscopic evidence in Part II, that meaning the stuff that we can't see, the atomic and molecular level. So let's start with our macroscopic evidence. Hearing that this is a chemical reaction, knowing that macroscopic evidence are the observations that we can make, you should be thinking of cats tell stories of ghosts. CTSOG reminding us of those 5 possible pieces of macroscopic evidence. Remember, you need at least one of these pieces in order to support that this is a chemical change, but to be really detailed, we want to list as many as possible. C stands for a color change, or if there is light produced. In this case with our Hindenburg, of course there is light produced coming from the fire. T stands for a temperature change. I can imagine, even if I wasn't there to feel it, that there must have been a lot of heat coming off of that fire as the Hindenburg caught on fire. S is a little tricky here. S stands for a solid being formed. In our Hindenburg, there actually was a solid being formed. That solid would be ash that you often associate with fire. O would stand for an odor produced. Although we weren't there, you could imagine that this was probably a pretty smelly fire. For example, if you've ever been camping and built a campfire, there's a smell that's associated with fire. And G stands for a gas being produced. Indeed, in this reaction, there was a gas being produced. That gas was water vapor. And if you forgot that, you actually could have scrolled down into Part B and realized that this reaction yields water. That water is water gas being released from this reaction. So in this example, there's actually 5 macroscopic pieces of evidence. Very, very important to include is that these macroscopic pieces of evidence, they came from the reaction itself. In other words, they did not come from any external sources. Taking a look at the rubric for Part A, if you got some macroscopic evidence and you explain that evidence, something like mentioning that there was a fire, that would have earned you a 3-4. If you went deeper into cats tell stories of ghosts and you got most of that macroscopic evidence and you explained how it relates to the Hindenburg, that would earn you a 5-6. In order to earn a 7, you really need to be getting all of that macroscopic evidence, all 5 of those cats tell stories of ghosts, and adding that detail that our cats tell stories of ghosts came from within the reaction itself, that it didn't come from external sources. Moving on to our microscopic evidence, this is the stuff that we can't see. This is our theory of what's happening in the really tiny level. The most basic thing to notice is that there is a new substance being created in this reaction. Okay, moving on to part II, the microscopic evidence. This is the really tiny stuff, the things that we can't see, like atoms and molecules. The first thing that you should be realizing is that there is a new substance being created. New substances being created is evidence of a chemical reaction. Again, if you had forgotten what exactly is happening in the Hindenburg, you could have scrolled down and seen hydrogen and oxygen yields water. When I say a new substance is created, I mean that hydrogen and oxygen created water. And so this water, H2O, is a new substance that didn't exist before. If you said something about a new substance being created, that automatically showed us that you understand the basics of the microscopic evidence and could earn a 3-4. To improve this answer, you could have started using key vocabulary such as atoms and molecules. For example, saying that the hydrogen atoms and the oxygen atoms formed a new molecule, H2O, water, could have been a way to work in vocabulary around atoms and molecules. That could have helped you earn a 5-6. In order to earn a 7, though, you really need to have a deep understanding of what is happening to those atoms and those molecules. This is where you could bring in the fact that you are breaking bonds. Or another way of saying this is breaking intramolecular forces in the reactants. And then you are forming bonds. Another way of saying that is forming intramolecular forces in the products. Showing that deeper understanding of bonds and or intramolecular forces would have earned you a 7. Moving on to part B, you are asked to write out this chemical change in symbols and then making sure that that reaction complies with conservation of mass. Okay, so we are told that we had hydrogen and oxygen, which yields, so I'm going to use my arrow, yields water, and you should be able to write water as H2O. Now, as I'm writing hydrogen and oxygen, though, I'm reminded of my diatomic elements. My diatomic elements, when they are alone, they always come with a subscript of 2. They always come with 2 atoms. This is where my Hofbrinkel acronym can remind me which of those elements are diatomic. So I see in my Hofbrinkel that H, hydrogen, and O, oxygen, are both diatomic. And because they're alone here, that means I must add subscripts of 2. This was a very common pitfall on this assessment, remembering your diatomic elements and applying that 2 subscript when necessary. But we are not done yet because this equation does not yet comply with conservation of mass. Let me show you why. If I write out my atom inventory, H2 and O2, and in my products, H2 and O1, you'll notice that it looks like an oxygen atom has disappeared in this reaction. But we know that's not possible. Conservation of mass tells us that mass can't be created or destroyed. So in order to make sure that our equation complies with conservation of mass, we need to make sure that we write a balanced equation. So I'll balance that up for you by adding some coefficients. By adding those coefficients, now we can see that conservation of mass is played out here. Looking at the rubric for this first part of question 4b, we see that in order to earn a 3-4, you must be showing conservation of mass. So that means that you must be presenting some sort of balanced reaction. In order to earn a 5-6 though, you need that balanced reaction, of course, but you also needed to recognize the diatomic elements. Now, if you presented us with a reaction that wasn't in compliance with conservation of mass, meaning that it looks like mass was magically created or magically destroyed, that would constitute a 1-2, that you lack an understanding or there's not evidence of your understanding of expressing a chemical change in symbols while also complying with conservation of mass. To finish up this question, in II, we are asked to identify the reactants and the products. The reactants here are what comes before the yields. So our reactants are going to be hydrogen and oxygen. And your products here, well, really there's only one product, which is water. We accepted you writing out H2 and O2. We also accepted writing H2O. Any expression of the reactants and products was good here. And in order to earn credit, anything above a 1-2, 1-2 would be like you didn't show understanding of reactants versus products. But if you correctly identified those reactants and products, that put you into the meeting expectations. Continuing on to number 5. Number 5 is talking about a situation we discussed way back at the beginning of the year in Unit 1, glasses fogging up. And it is telling us that this is a physical change and asking us to provide evidence both macroscopically in terms of stuff we can see and microscopically at the atomic and molecular level. Notice that this question follows a really similar structure to our last one, but now we're dealing with a physical change instead of a chemical reaction. The first important thing to realize about what's happening with glasses fogging is that there is a phase change going on. And that alone, we know that phase changes are not creating new substances, they're just changing between solid, liquid, and gas. So those phase changes are automatically going to be physical changes. Now you could dive deeper into what type of phase change is happening. And here we have the gas-water vapor that exists in this guy's breath. That gas-water vapor is hitting the cold glasses, reaching the point of condensation, and it condenses into liquid water droplets. Taking a quick look at our rubric at the same time, mentioning that it's a phase change would be a 3-4 category. Understanding that that phase change is a condensation going from gas to liquid would be a 5-6. But what many of you did is went the route of Cats Tell Stories of Ghosts. For Cats Tell Stories of Ghosts, it was pretty clear that there was no gas really being created here. Some of you commented that the person's breath would be gas. I suppose that's true, but really there's no new gas that's present. There's probably not much of an odor. Maybe there's an odor, he has some bad breath, but we kind of understand why that might be so, not coming from the reaction. Definitely no solid, no crystals being formed. Some of you said there might be a slight change in color. The glasses went from being clear to like foggy and a little bit white. And some of you commented that there is definitely a temperature change. That temperature change comes from the hot breath hitting the cold glasses. So there is actually evidence of temperature change, maybe color change. You could argue a few of the others, but the important thing here is to recognize that any of these changes that you're observing come from external sources. They're not coming from the phase change itself. There's a temperature change because that glass is cold because it's cold outside. The weather that day is cold out. Or there might be an odor change because that person has bad breath. Not because our water in our breath condensed into liquid on the glass. All of these changes can be explained by external sources. Recognizing that there are those changes present, but that they don't really count because they're external sources, that would be a 7. And for part B, the microscopic evidence. First and foremost, you need to recognize that there is no new substance being formed. That alone could earn you a 3-4 to recognize there is no new substance. That shows us evidence that you are understanding what a physical change truly is. Being more specific and diving into the fact that you had H2O, that you had H2O as a gas in the person's breath, and that H2O went to being H2O in the form of liquid on the glasses is a more specific way of discussing what's happening here, showing that there are no new substances. So this is really describing the gas to liquid, and we would love if you would use some key vocabulary like condensation. It's so strange. To really finish off this answer, in order to earn a 7, you would need to dive a little deeper to discuss that there are intermolecular forces being formed. That we are going from a gas state where the particles are spread out, and there are pretty much no intermolecular forces. Recognizing that that is being changed into a liquid state where your particles are closer together. And there are more intermolecular forces. Those intermolecular forces were formed through the process of condensation. So discussing the intermolecular forces, you could also talk about how the intramolecular forces did not break or form here. The chemical bonds were not broken or formed, would also be great. And finally, our last question, question number 6. It says, consider the chemical reaction below. You are given the reaction itself. You're also given a picture of the reaction. And you're shown this reaction happening before and after on a scale. It says, explain how this change in mass has occurred. And you could use claim evidence reasoning format to help you communicate, although you didn't have to. The first thing that comes to my mind here when I see a change in mass is really conservation of mass. Conservation of mass says that mass can't be created or destroyed. Here, you're noticing that our scale went from 3.9 grams down to 2.85 grams. So we're noticing a drop in mass, but it's important to recognize that we can never violate the conservation of mass. So this drop in mass, that mass had to go somewhere. It didn't just magically appear. It didn't just magically disappear. It had to have gone somewhere. So where did that mass go? Well, if you take a closer look at this reaction, you can see that one of your products is CO2, or carbon dioxide. From your experience, you probably know that carbon dioxide is almost always a gas. In fact, this is supported by some observations I can make about the bubbles being inside of our beaker. those bubbles trapping that carbon dioxide gas. So discussing that the carbon dioxide, the gas of carbon dioxide, was part of the products, or pointing out that there were bubbles that you could see or observe in the reaction, that's going to be the other key piece here. So if you mentioned conservation of mass or a gas being released, that would be a 3-4. This would be conservation of mass or a gas being released. If you mentioned both of them, conservation of mass and a gas being released, that would be a 5-6. But to really take this question to the next level, to earn that full 7, you need to be really thorough in your understanding. You could demonstrate this by making a connection that the gas, or the CO2, has left the beaker. It has gone into the atmosphere. And therefore, it's not included on the scale's reading. Or maybe discussing how if you had put a lid on top of this, that you would have seen different readings on the scales that would show mass all being the same at the beginning and the end, because you would have trapped that gas in and had that gas be part of the measurement. So being really thorough and making those connections could have earned you a 7 here. So those are all of the questions on this test. Remember, as we determine your overall grade, we are not averaging. So if you go through and try to average each of your grades together and you wonder why your overall grade doesn't match that, that is not how we're determining these grades. These overall grades are a best fit model. So we are weighing what evidence of understanding did you show us, where could you have improved, and coming up with a 1 through 7 score that best represents your overall assessment. As with any assessment, once you've watched this video, if you still have questions, feel free to contact your teacher, get in touch with them to discuss those questions, because we always want to make sure that we're using key assessments as learning opportunities. So yes, your grade has been determined, but how are you going to improve moving forward? What should you continue to do that you're doing well? How might you want to change your approach to studying and taking assessments? These are really important things to think about and kind of entertain that metacognitive space so that you can continue to improve into next semester.